Welcome to our class. Today I want to look at how to deploy and verify contracts on BES. We're looking at BES Sepolia, and you could also use the same tactic to do work on BES mainnet. But in our previous class, we looked at how, first of all, to fund our BES Sepolia with test ETH. Free ETH that is required for deployment and verification of our contract. So we pick up from that lesson today, hoping that you have your MetaMask account with the free 0.1 test ETH. So with that, we will now proceed to deploying and then verifying our contracts to BES Sepolia. And then after that, we do some interaction. We interact with our contracts on chain. Of course, I'll also be showing you how to interact with it off chain using Foundry. Of course, we can do it without necessarily having to write scripts, but in our next class, we'll look at how do we now write scripts and automate the whole process of deployment and verification of contracts on BES Sepolia. So in our today's class, I'll just be walking you through the workflow of deploying, verifying, and testing zero-knowledge proofs, verify a contract on the BES Sepolia testnet. And among the things we'll cover, we'll see how, first of all, the verifier smart contract is generated from Noir. And this, most of you are familiar because we've been doing it. We've been doing this, generating smart verifier smart contracts from Noir circuits. Then after that, so that will just be a recap of what we already know. But then from there, we'll look at deployment, how it's handled using Foundry. This time we'll not be automating the process using scripts, but in our next class, that's what we'll be doing. We'll automate the entire process. After deployment, we'll look at verification, how it's done automatically. Of course, on BES scan, and we'll be using Etherscan style API key, which I showed you how to obtain in our previous class. So I also assume that you already have that. You have the Etherscan API key. If you don't have it, you can revisit our previous class and see how to obtain it so that when it reaches a time to use it, you will be having it. I'll then take you through how proofs are generated using Noah's backend, that is a BB proof, and then how they are then verified on chain. Of course, what we'll be verifying on chain are those ZK proofs. We deploy the contract and we use that contract just to verify the proof that our ZK proof was correctly generated and therefore can be verified. So therefore, by the end of this session, you should have a full proof to chain pipeline. Should have that pipeline operation on BES Sepolia, right from circuit generation, a proof generation, then a deployment of the contract after we generated it, then verification. You'll have the entire workflow by the end of the class. So among the objectives we're looking at, one would be to configure the environment and the tools for BES Sepolia deployment. And 2, deploy a Noir generated verifier contract using Foundry. And then 3, verify the deployed contract on base scan. 4, generate a proof and the public inputs with the Noir and format them for on-chain verification. Of course, you understand what public inputs are. We also have the private inputs. And we already said that the public inputs will be known to both the prover and the verifier. So, but the private ones are only known to the prover. They are not, we do not require them in this workflow. We only require the public inputs. Now, the last objective will be to interact with the verified contract on a base scan by the Foundry CLI. So straight away, let's look at the environment setup. That is what is required for this class, what you're supposed to have, what you're supposed to have learned, the prerequisites for this class. So that means just mention them. And if you do not have them, you can always visit our previous class where we covered most of this, in fact, all of them. We're required to have Foundry. I'll give you a link on where you can look for more information on Foundry, or you can also visit our previous classes. We also require Noir from Noir. Alchemy, in fact, what we only require here is the RPC URL, which I showed you how to obtain. And then you also require the Etherscan account API. This one is used, this key is used for verification. And I showed you how to get that, so you need to have it. So we need to have these 4. Once you have these 4, we are ready to proceed. In our previous class, we had ended with coming up with the environment variables, this .env, where we got our private key from the MetaMask, and then also got our RPC URL from Alchemy, and then got our Etherscan API key. So that means you should be having these 3. And we had already written our .env. We had already had our file. So that you compare with yours to see that it has what it's required to have before we we had said that the private key, which is in your .env, must be well kept so that it's not exposed to the public. But again, I said you could also use an account that does not have real ETH, just to ensure that you are safe when you expose this private key to the public. Like mine, I'm just exposing it because my account does not have real ETH. Now, so this is .env, what I'm sharing. And from what you can see, it has the private key. It has the RPC URL. It has chain ID. And then it has the Etherscan API key. And all these, we did them in our last lesson. We got all these keys in our last lesson and created this file. Now, remember, this file is not supposed to reach to your GitHub, and therefore you add this command just to ensure that it goes to your gitignore because of the security reasons. Because of you're protecting, because you're supposed to protect the private key. So should not go to GitHub, should end up to the gitignore. So this command does that. Now, good. So this is the .env, but we had looked at this last time. Now, after you've gotten your file .env, you can always activate it using source.env. We also had done that already, but there's no harm in repeating it. Note that there's some space between this E and the dot, and that space must be there. Then after that, we have env. Now, once you have the .env ready, you now write a script for deploying. Okay, so before just you write a script, we can deploy this just locally. So if you wanted to deploy it locally, then you just run this command, and then you will deploy that locally. But if you want to deploy it on chain, that is now when you write a script that be showing you how to write. But you cannot just deploy it locally. So you can try those commands I've shown. Try those commands and see that you can deploy it. Now, I also want just to do it locally so that we move together. Now, so to do that, first of all, you should be in the folder contract, because that is where our verifier.sol is. So cd contract. Now, once you're inside the contract, you can now use this command. And this command, you just replace your correct RPC URL, replace your private key, replace your Etherscan API key here, just replacing the whole thing, beginning from the $sign. Then you run this command in your terminal. So let me just also replace my private key. So I just replace my private key here, beginning from the $sign, then replace the RPC URL, replace it here. And then I have the Etherscan. I'm doing this because I want to deploy and verify at the same time. That is why you can see I have Etherscan API and then I have verify as a command here. Otherwise, if you only require it to deploy, then these two are not necessary. But you want to do deployment and verification at the same time. So we require those ones to be part of. So after replacing, you just paste it in your terminal and press enter. So you can see mine is deployed. So let me just show you my terminal so that you can see the output. Now, beginning from here, it gives you the deployer and then the address to where it's deployed to. So if you are to check this online, you can still find this contract deployed there. Then there's this hash. And then it says starting verification. So deployment has ended, therefore it begins to do verification. Then waiting for and so on. We have all that information there. But now very important is that after verification, it says submitted contract for verification. It gives the response, says okay. Then this guide, remember in our last class, we said how important this guide is in the process of verification. And then again, where you can find the verified contract, the address is given here. So it has been deployed and verified. You can see the response is okay. And then details pass verified, and then contract successfully verified. So we did deploy and at the same time verify, but we're doing this manually without any script. So it's possible to do this and go on chain and just check at the address given, and you would see your contract there deployed. Okay, let's try this. We are given some URL here, URL. Let's try to go there and see what we get there. So I'll share my browser. So I'll stop sharing what I'm currently sharing and then share my browser so that we just see that what we've deployed can be seen online. So I copied the URL and then I paste it here, press enter. And when you do that, you can see this is the best scan. And the contract is here. And you can see it's green here. And green here, when I point at it, it says the contract source code has been verified to match its on-chain bytecode. Source code verification does not imply the contract is safe to interact with. That is no problem. The thing is, once you see it's green, it means it has been verified. So it's already on-chain. We did that manually, but you can also see the time we did it. It's 3 minutes ago. It's indicated here. 3 minutes ago, we did deploy this contract and then verified it. So when you click on this, you can see there's some check mark. So when you click on this contract, you will see the exact verifier.sol that we had on our local machine. So this is the exact verifier.sol that we had, but is now on chain. Is now on chain. Now, later on, we'll come and see how to interact with this. Contract by just clicking on this read. Right now, you can see when I click on read contract, you can see something saying connect to Web3, then read contract, and then verify, and so on. So we'll come back later to see how to interact with this. So by interacting with the contract, it just means being able to read the contract and then write contract here. It says write contract. And before it was read here. So we'll come back and see how then to interact with this contract in the manner of reading contract and writing contract. Now, again, I just emphasize that what we did deploy, we did it manually, but we can always automate this process. And that is what we'll be looking at in the slides that follow, so that we are not doing it manually. But again, there's no disadvantage of doing it manually, just as we did. It will still be deployed because that is our target, to have it deployed on chain so that we can verify our proofs and so on. Now, good. So come back and see what the command just did. Now, first thing the command did, it compiled the verifier.sol, and then it deployed it to base Sepolia via the Alchemy RPC URL, then automatically verified the source on Basecamp. So verifying just means that, as we saw, that the source code agrees with the source code agrees with the on-chain bytecode. That's what it means by verifying. So once it's verified, it means they have confirmed that the source code, whatever you have on your local machine, agrees with what is on chain. Now, there's something here. For you, you may have encountered an error. For me, I did not. I did not encounter an error because I had already worked on my Foundry .toml. I'd already worked on my Foundry.toml so that it can optimize the size of the contract. Remember that without these optimizer settings, as we've seen in our previous classes, without these optimizer settings in our Foundry.toml, you would have a contract that has a larger size, larger to the extent that it cannot be deployed. Because for deployment, there's some limit for the contract. The contract has to have some limit in terms of size. So if it goes beyond that, it cannot be deployed. So to ensure, because when you're using Noir, every time you generate this verifier.sol, it will be of larger size. Every time the size will be large. So that means you have to always add this command inside your foundry.toml. So you just add this if you had not added, and you are able to deploy. Otherwise, without adding that, you will not be able to deploy because of the larger size. So my foundry.toml is here. And what this is not necessary. What is here is not necessary here actually. What I'm talking about is this part. Optimizer settings. Optimizer true. Optimizer runs 200. And then I think these two here are what will make your contract deployed. Without them, there will be no deployment. Now, so let's now assume that to this extent, you have deployed because you already have edited your foundry.toml to have the optimizer settings. And we've done the deployment manually. And we are now ready to do deployment automatically using a script. But before that, we just look at the deployment summary, although we had already looked at it. It gives us the deploy address, gives us the contract name. So the contract name is not verified sol, but Hong verifier. Then it gives us the address to where the contract is deployed, gives us the hash transaction, then the network, the Sepolia in this case, and then verification tells us whether it passes or not. In our case, verification passed. Now, we now want to use a script to do deployment again, so that we have various ways of how to deploy. And this use of script is most important, especially if you are doing your deployment frequently. Supposing you're a person that deploys most frequently, then what you require is a script just to automate the process. But if you just deploying once in a while, then the first method that we used would still be enough. Now, so the script that I've attached here is what we will use to automate, and it's created inside a contract script folder. So inside your contract, you create a folder called scripts, and then inside this folder, you create a file called deploy.s.sol. And inside the file deploy.s.sol, you paste this code. This is what will assist us in automating the process of deployment. Now, this script is not new because we've used it in our previous class again, when we were deploying on Ethereum Sepolia. We are just deploying on Sepolia this time. So the deployment script is just the same. Now, if you have the script already, then we again want to deploy and verify at the same time. So this again is the command. Slightly different from the previous one because of deploy.s.sol here, because this is now a script. one did not have this, but the other commands remain the same. Let me just take you back to the previous command. It's here. We had forge create verifier.sol, and then the name of the contract, Hong verifier. So this is where the difference comes in. Only this part, but the rest are the same. So this one you are doing it manually, but this other one we are doing it, you're automating the process. They're using a script, deploy.s.sol. So the other commands remain the same thing. So let's again do that. It must be inside contract, CD contract. Now, this is what I'm referring to. We have contract here. Inside the contract, when you right click, there's a new folder. When you click on this new folder, it gives you somewhere to type, you type script. So you have opened a folder called a script. For me, I have it here. Then inside the script, you can also right click and create a new file. And this new file, call it deploy.s.sol. Now, this deploy.s.sol, you paste this code. That's what I'd say. So once you have done that, then we can always use the command I gave to deploy. Okay, I also want to do the same thing. The command I'm referring to is here. So we only need to replace our RPC URL. So I just copy my RPC URL here and replace it together with, replacing this together with the $sign. It's the RPC URL. Then replace the private key, again, copy it and replace. Now I've not added Etherscan. Oh, it's here. Etherscan is here. I think I had forgotten it. So copy the API key and replace this part. Then now, with the entire code, you run it inside contracts. For me, I'd already deployed this and verified, but I'm taking you through the steps so that you just follow the same steps. You can see it has been deployed. It has been deployed. There are logs here. The logs say verifier deployed at, so we are given the address to where it has been deployed to. Again, the chain ID is given to us. estimated gas price given to us. But remember, for us, we're using free ETH, which we loaded in our previous class. And then estimated total gas used, estimated amount required. This is the estimated amount required. Given the hash, and then the address to where it has been deployed. This address is the same as the one we saw earlier. Then paid, total ETH paid. After that, so that shows that it has been deployed. But then after deployment, there was verification. And you can see on-chain execution was complete. Start of verification. Start verifying this contract. The contract that it was deployed at this point. So then it begins, verification process begins. We've been given the optimization, of course. This is what we entered in our foundry.toml. Submitting verification for verifier.sol, Hongo verifier. This is the name of the contract. The response was okay. Again, we are given the guide and the URL. We will go there to see our contract. Now you come here and you're told details, the status of verification. The response is okay, details pass, verified, contract successfully verified. All contracts were verified, and we are told that there was only one contract. If you want to see the details, they are saved to inside your contract. When you click on it, you'll see broadcast, a folder, then inside that you'll see deploy.s.sol. Then inside that, you'll come and see run latest. So what I'm referring to is our contract. Inside this contract, you'll see this folder called broadcast. And inside the broadcast, you can see deploy.s.sol. Then we have 84. This is the ID of Sepolia. Then inside that, you have run this.json, run this.json, and so on. They're all here. So if you want them, you can always find them here. Well stored. So they only are generated when you do the deployment. Now, I've noted here that this command does everything in a go, in one go. What that means is that by this command, you're able to compile, you're able to deploy, and at the same time verify and log the contract address. So this command does all those: compiling, deploying, verifying, and logging the contract address. Now, when we went through the summary, this is what we saw: the deployer, the contract name, the deployed address where it has been deployed to. Of course, what I'm using here is for the previous one that I deployed previously, but now they've changed because we've done a new deployment. So again, this address and so on would change, or specifically the address and the transaction. But this will be the same because this is my account number. This is the account of my MetaMask account. So the rest would remain the same. The only difference is here, every time you deploy, you get different results at these 2 points, the deploy address, the deployed address, and the transaction would be different. We've seen this, the output where it was saved, inside broadcast, we've looked at that. So what this therefore means is that your deployment is now live to base Sepolia, and that verification used the Etherscan API and was done successfully, and that the contract source is now publicly verified. Is now publicly verified, and therefore developers can inspect and interact with it directly on Basecamp. If you want, again, you can also view it on chain because it's already public and verified. Now to view it, you would just copy this part up to here and replace the remaining part with your deployed address. So this is what you just copy from my code, from these notes. But the other one, the other bit, you would replace with your deployed address. So that's what we want to do. So again, I want to share my browser. So this is what I said we share. Now I want to copy my deployed address. So you can also use yours. The deployed address for me is that. Then press enter. Here it is. You can see it was deployed 9 minutes ago. The contract has been verified. If it would verify was not there in our command, then this would not have been ticked green this way. And again, when you point here, you are told that the contract source code has been verified to match its on-chain bytecode. Again, as I had already said, that if you click on this, you're able to see the exact verified sol that you had on your local machine. Compiler version is here, and then the name of the contract, the Hong verifier. And then we had optimized. So everything is here. What remains for us is just to come back and interact with this contract by reading the contract and also writing the contract. But before that, again, I should say there are various ways of doing this, interacting with this. We can do it here on chain, or we can do it on our local machine. So we will do both step by step. Now, there's something I've noted here. I've said that verification badge, if it's green, if there's a green check mark, and we had already seen that, it implies that the contract source is verified. So what this means is that your Solidity code, in other words, the verifier.sol, or the contract Hong verifier that you had, is now publicly merged to the on-chain bytecode. That's what it means. Now, you may also want to see the transaction details on chain. If you want to see the transaction details, then you would copy this part up to here and replace the remaining bit with your hash. So just go to your logs and you'll see hash. Copy that command, that whatever is there, and replace this. And we are doing that again in our, browser. Just want to show what the hash is. We had seen it before. So when you come back here, you can see this hash. So you can copy it. In fact, the other command, the other URL was here, the one we've just seen on our browser. Here it is, it's always here. So you can copy it and just use it. But let's now see the transaction details. So we've just copied the hash, and then you copy the other bits from my notes, the other parts. Let me share my browser. So this part only shows you the transaction. You can see it says transaction details. So the hash that we just used is the one I'm seeing here. It tells you that status is success. then confirmed by sequencer 14 minutes ago. Then this is my contract, no, my account. And then this is the address to where the deployment was done. Just click on it. So when you click on it, it takes you to the contracts. It takes the contract, just go back. What if I click on this one? I'd say this is, yeah, it brings you here. And this will be showing you, this will be the details of all my transactions, what I've been doing with my account. You can say I did this 15 minutes ago, did this 34 minutes ago, then 6 hours ago, and so on. Because this is the same account. This is my account. So these are the transactions on this account. So age is just the time when the transaction happened. What about if I click on this? It brings me here. So you can try all these things. You can try and see what happens if you click on which one, and so on. It says click to show more. So if you wanted to see more, then again, you just click there. But that is not my interest. My interest is to see, to go back to where we deployed so that we do read the contract and write. So we'll be coming here to read the contract and write. So that is where my interest is. Now, so that one takes us to our next agenda, which was to, our next objective was to interact with the verified contract. We already have it. We have it verified. So what follows, therefore, is just I guide you through the process of interacting with your verified contract. Now, this is important because it lets you to test your verifier right from the Explorer, and that we do not require Foundry or script at this stage. It's not necessary, but you may use them if you want, but it's not necessary. So when we went to our contract, you're able to see there was a place read contract. This is where we proceeded to read the contract, and then we will select verify. There was a place verify. Then on the verify, we're supposed to paste our proof. Our proof is inside our target. In our local machine, we have circuits, and then we have targets. Inside the target, we have proof, and you have public inputs. Now, what you discover that is that what you have, the proof that you have currently is not one that can open because it's binary, but we'll be converting it to hexadecimal, and I'll show you how to do that. And then that hexadecimal is the one we shall use is the one going to use to copy and then paste in the spaces will be given. Now, once you do that, you would say query, and once you query, you would see something like bool true. Now, what bool true means is that your proof is verified successfully on chain, because that is what you want to do, to just verify your proof, your zero knowledge proof on chain. Before we do that, again, I'll just take you through the steps. First, we're going to read contract tab, then click on read contract. And this, when you click on that, it lets you to query or view contract data without sending any transaction. So there's no transaction required. You just want to view the contract data. Now, this table is just a summary of what you can do and what you cannot do. The action, for instance, here you can test the contract structure by just inputting data. And then this is what you cannot do. You cannot paste your actual proof binary like the one we have. So that's what I said, that the proof we currently have is binary and therefore we cannot paste it. So what we will do, first of all, will be to convert it to hexadecimal, and then copy that hexadecimal proof and paste it. You can run the verification locally via script, and this is a recommended way to pass the real proof and public inputs. Now, before we go there, we'll just remind of how a proof is prepared. We do generate proof. For us, we've done yarn generate proof, and we've also generated proofs manually and using some command. And we've done this quite a number of times, so this is not something we should again venture into because we've done it before. But once you've generated that proof, it will be inside the targets. And then there will also be public inputs there. But we want to convert the proof that we have to hexadecimal. So this will be the command, and that is where I want us to start from. So let me just share. Now this is my target. Of course, it's inside the circuit. So when you click on circuit, you find target here. Inside the target, we have proof, and we had done this generation of the proof earlier on. We also have public inputs here. So you can see the proof. It says when you click on it, the file is not displayed in the text editor because it's either binary or uses an unsupported text encoding. What about the public inputs? The same thing, but what about this one? can see some public input here. There's no problem. Want to begin by processing our proof. And I had just shown you the command we're going to use. So our proof is inside circuit. So we get inside circuit. Then while inside circuit, you get inside target, because that is where the proof is. Once you're inside the target, this is the command I'd given you to, just a minute. Oh, I deleted my terminal. There I have it. So with this command, when you run it, you can see that I've created proof hex. Proof hex. When you click on it, you can see some proof here as a hexadecimal number. The only thing it's lacking, OX, or is it 0x? It's lacking that. Also, when you look at our public input, it begins with the 0x. So this is how a hexadecimal number is supposed to begin. But now for our proof that we've just generated in hexadecimal, it lacks the 0x part. So that is the only thing that is lacking. Okay, but that is no problem, because we will come and create the proper one. Now, after generating that, you need to know what the double X D, then dash P does. This part of the command. What does this part of the command do? The XXD space dash P, what does it do? Is important. It creates a plain hex dump. It creates a plain hex. So it creates a hexadecimal number without OX. That prefix, that's what it means. So it creates without the prefix. But Solidity Verifier would expect that a hexadecimal number would be a string with the OX or a 0x. Now we can inspect where the start of the hex string, although this is an optional process, is optional, is not important, just inspecting where the start of the hex string. So by use of this command, pasting it in the terminal, let me just do a correct command. This is the correct command for inspecting where the hex begins. So when you press it, you can see where it begins and where it ends. So let's just scroll down and see whether that is how it ends. Okay. So because it's a long thing, you cannot see where it ends. So that is not, I said that this is an optional process, is not mandatory and is not even a must, is not important. You can also want to view your public inputs. We had already done that when we just pressed on public inputs. But supposing you only had the binary one, because you can see in our case, you can see that in our case, we have this, which we were able to see, and there was this, which we could not be able to see. Supposing you only had this, how would you have seen your public inputs? So you can do that by just pasting this command in your terminal, cut public inputs, and you can see your public inputs are here. They're here. So if you only had this binary one, you would still have done cut public inputs, and you would have seen your public inputs. Now, and again, that is not very important, but we require those public inputs because we'll be using them. Now, let me just take you back to our contract, first of all, on chain, that you see why we require the proof and the public inputs. This is where it was, this is where we deployed it. And when you clicked on the contract, you had this. But I decided we come here to read contract, press on it. And when you press on it, you have this part. Now, let's first of all connect to Web3. There's this warning, but it's not a bad one. You just click OK. Then it asks you to connect MetaMask or whichever that you use. For me, I normally use MetaMask. And you can see it's connected. This one is connected to Web3. My account is here. Now click on verify. Click on verify. When you click on verify, you are required to enter your proof here in bytes, hexadecimal, and then you're also required to enter your public inputs here. And then you query. So when I query right now, it tells me invalid number of parameters. So I've not entered my proof and I've not entered my public inputs. And that is the reason why. So we require the proof. So already we've generated the hexadecimal proof, but in the format in which it is, let me just see, just copy in the format in which it is. So that I show you that it is in the format in which we have it, it will not work. I'm just copying the proof hex, the one we generated without OX, without 0x, and then I paste it inside the proof. So this is the proof. Then I come and again copy the public output the way I can see it here, just the way I can see it, and paste. I just want to show you that this, the way I'm seeing them, they will not work. When I query this, you can see there's an error. You can see there's an error. And when you come at the bottom of the error, or even here, it says invalid array value, argument, and so on. Now, the problem is our proof. It lacks the OX, and again, is not a continuous line. It's not supposed to have spaces. It's supposed to be continuous. not to have spaces. Now to generate I've noted here that to generate a single line proof with the OX prefix, which is recommended, we'll use this command. And then after this command, we will verify the formatted proof so that we can just see it and copy. We can verify using this. So let's just go back to okay, we are back here. Our proof is inside our target. So let's get inside circuits, then get inside target, and then use the command I just showed you. Want to generate one continuous line of hexadecimal proof. Press enter, and you can see something here, proof formatted hex. And you can see it's one continuous line, and it begins with the OX. This is the proof we require. So you can copy it. You can copy it. After copying it, let's go back to our contract. And then where there's a proof, change what we have, replace it with what we've just obtained. And after that, we can say query so that we see what the error is. Now, the other thing we're supposed to do on these public inputs, remove the quotes, remove the quotes, remove the quotes, and then query. Okay. Let's come back to there's something I had told you. After generating this proof, let me just take you back again. Let's cut the proof from the formatted proof. Let's just cut it. I'd said to verify, you would need to cut. Let's see. Because I may have copied something incomplete. So let's now copy this from here because I can see the end of this proof. I can see the end is this 0. I want to copy to the start of it where it has begun. And it began from 0x here. This is where it began. So again, let's go back on chain. And replace what we have. I hope I've replaced it. Then what about, I think the problem is now on my public inputs. So let's extract our public inputs in hexa. We had said cut public inputs. It said cut public inputs. CD circuits. Let me copy the way it is. But remember, we will delete the quote, the quotation marks. Remember that this is different from what we just deleted. Let's again generate this contract. Now the proof. Let's again deploy it because I think we are using a different, I had deployed several contracts. So I think we're using a previous one. You just want to deploy and then go straight to interacting. So that we go straight so that we don't use a different link. So I'll delete this. We'll recreate another one. Then delete this. need to replace a private key. Then replace our Etherscan API key. And then replace our RPC URL. RPC URL. Then copy the entire thing here. Get inside circuits. Then inside, we want to deploy. We want to deploy, so we get inside contracts, not circuits. We're inside contracts. Now we can deploy and verify at the same time. Now this is where we deployed it to. The address is here. So this is what we're going to use. So these are our newly deployed contracts. Go straight. We've already deployed and verified it. So we go straight to our browser. And here it is deployed 1 minute ago. So let's come to contracts, then read. Connect to Web3. And then verify. So we go look for the proof. We have binary proof. We say the first thing we do is to convert it to hexadecimal. And we must be inside circuits. And inside the targets. While there, convert to hexadecimal. You can see proof hex. We're not interested with that. What you want to do, first of all, is to now create a single continuous line and to do that, we used this command. It has done that. So you can see our proof is now a single continuous line, but let's cut it so that we can see the beginning and the end of the hexa proof, and then copy that. And you can see the end is here. So I just copy the end to the beginning is there, and then go back to our browser. And paste the proof. Let me delete it first of all. Just want to be sure I'm beginning from the very end. And paste is okay. Now we want to go back and cut our public inputs. Just come down and paste here the command for cutting public inputs, and we can copy it here. Remember, we will do without the quotes. So we go back to the browser. And paste the public inputs. Just remove the quotes, then query. There's still this error saying ran out of gas. You might also see error. Okay, we can also do it on chain. Now, we can also do it from our local machine. Then we see what happens. Because I think it's because I had already done it on my side. So maybe repeating it, doing it a second time is what is not working. Now let's use this command just on our machine, but this time it should be inside the contract. This command, let me just copy it. I will make a few changes on the command I've just shown. Remember, be inside contracts. The command I'm referring to is this. So we'll change, what you're seeing here is the address to where it was deployed. So I can just go back here and copy my address, go back to on chain where I copy my address and change. This is my address. And then this is the public output, public input. You replace this with the proof, the hexadecimal proof. The whole proof. Let me first of all replace the URL because the proof is very long. It will push the whole thing very down. So RPC URL, replace it. Then now replace the proof. You copy the hexadecimal proof, the one we just generated. We want to see whether it will work on our local machine. If it does, then it means that we are out of gas as it suggests. So that is my proof. Okay, so let me copy this and paste it here in the terminal. I don't know how many times I pasted it. Let me just run. It's not pasting. Yeah, it's now okay. Pasted once. The other time I pasted several times. Since it's long, it was taking time to paste, but you can see at the bottom, it has said true. So that means the verification has been done. And I don't know why the same thing is not happening. I think it's because of the gas, as it says, because it's able to, the same public inputs and the stuff is working locally. So it's supposed to even work on chain, supposed to work on chain. So I think it should be because of the gas, as it says, because when you press query, it says returned values aren't validated. Did it run out of gas? You might also see the error and so on. So I think that is the reason. I think it could be gas or something else, because the same public inputs and the same proof is working in our local machine. So it's supposed to also work here. So, and again, when I began, I said there are two ways of doing this, interacting. You could do it on chain here, come to read contract, connect, and then paste here your proof in hexadecimal and your public inputs again in hexadecimal. Then query, it's supposed to give you the same result as what we got in our local machine. So that is how you design a circuit in Noir, deploy it, and verify it on best Sepolia, and then interact with it. Thank you.